Welcome everybody to this next in the series of Applied Analytics seminars, and thanks for turning up. Today we've got George Despotou from Warwick, as you can see on the slides, talk to us about synthetic data and synthetic data sets. Usual mode of operation. But George will talk for a bit, and then if you have questions, if you can put them in the chat, and then I'll pick them up at the end, and I'll just act as kind of MC for the questions at the very end, to save George having to look at that. He just answer the questions. So if you're happy enough to head off, George, maybe you could take it away. Thanks.
Yeah, that's fine. Thank you, Dave. Hello, everybody, and thank you for joining this seminar. So this presentation is based on a project that we did a couple of years ago on synthetic data sets. And the motivation for the project was to use synthetic data sets for validating healthcare application as part of regulation. And I'll mention a few points about this as we go along during the presentation. First of all, a bit on the problem and the background. There are significant advances in digital health across numerous topics and aspects. We have diagnostics, self-monitoring, clinical decision support, telehealth. And all these innovations do provide benefits to patients, and they also use advanced IT techniques. So they use machine learning. They may use complex rules to provide clinical decision support, and so on. So with the increase in use of digital health, there's also an increase of concerns about the safety of those applications. And by safety, we mean technical safety, so ensuring that the application will not just crash when a patient is using it, and also the clinical validation of the application. So, for example, when we have an application that provides clinical decision support or provides some sort of recommendations, let's say a symptom checker, we want to ensure that the recommendation and the suggestion of the application is in line with clinical evidence, so that it does not provide subpar recommendations to patients. In order to achieve those two aspects of safety, innovators or digital health developers, whichever term you would like to use, need to have access to data to validate their application. And this is the big problem. Access to data is not easy, particularly when we talk about applications that need machine learning, or they need to train themselves into based on the entire population. These kind of data sets are not easy to access, and there are some privacy concerns about those data sets. So the organizations that do have the data sets are unwilling to share them because if there is a leak, then this may have implications to patients. And this results in lengthy processes and expensive processes to allow innovators to access the data that they need. And ultimately, this may deprive patients from innovations. So we need some sort of way to catalyze this innovation whilst maintaining the privacy levels that patients expect when they have consented to providing the data. And I just have an example of how high profile this kind of data breaches or data leaks can be, particularly in healthcare. So it is an important problem, and it does provide barriers to innovation. So synthetic data sets have been identified as a way forward, as a way to overcome this problem. So in order to, instead of using a real data set, we use a synthetic data set, which is a data set consisting of a completely fictional data points, which can be shared easily, if not freely, because they do not represent any real people. And this comes with a couple of asterisks, which we'll discuss again a bit later. So this was the aim of the project that we worked on. We wanted to facilitate safe and clinical valid digital health innovations using synthetic data sets that replicate the statistical qualities of real data sets. And the aim was to use them to prove concepts of healthcare applications, validate their clinical correctness, and to de-risk safety assurance for innovators. So whenever they start developing an application, they can use these synthetic data sets to have some assurance that they're going the right way. And the outcomes of this project was a method that generates realistic synthetic data sets and an assurance framework that was an initial attempt to look at how the evidence that we collect from this process can be used to support this kind of digital health applications. And just to acknowledge the project, this was a project funded by the Department for Business, Energy and Industrial Strategy, and we worked with the NHS Digital and also the MHRA, who were supervising the overall project. This is the method that we used for to generate the synthetic data sets. We made a series of experiments used to evaluate and evolve the method. So we had a number of steps, and we had the main steps of the method, which are the numbers. And then we had some steps that provide context to the machine learning process. And these were the scenarios of use of the dataset, the performance evaluation of the machine learning approach, as well as the assurance requirements. All these contextual steps provided requirements that, these are important steps because they provided requirements that affected how we designed our machine learning approach, what kind of statistical tests we would need to pick to establish equivalence between the two data sets, and understanding how the data set is going to be used. For example, if a data set is going to be used to provide recommendations for minority groups or outliers in the real data set, that becomes a lot more challenging than for the average population. All experiments use the generative adversarial networks, and I'll get back to that. So I'm assuming a lot of you are familiar with generative adversarial networks, but for those of you who aren't, essentially these are two neural networks in a configuration connected with each other. So we have the generator that generates some data, some of which data, let's say, represent the real data set. And some of these data that do not belong to the real data set, and we call them fake data. And then we have a discriminator, which is another neural network that trains itself to discriminate, to classify the data into real data or fake data. So we try to train those two neural networks until the discriminator cannot tell real from fakes. So this would mean, in theory, that the generator neural network provides data that are to the quality of the original data set. So this is the approach that we used. The literature supports this approach. It's used in other domains, for example, from statistics department, to create synthetic data based on census data and so on. So it looked promising, and after a few experiments, we confirmed that. And also, generative adversarial networks are used a lot with images. They're used a lot to create deep fakes. You've probably heard of them. But they haven't been used a lot for data like patient data. But this is picking up now as well. So we made a series of series of 6 experiments, each experiment adding complexity. So we started with a simple network with numerical values. Then we added we increased the data set, we added categorical values, we developed variations of the generative adversarial network. So each experiment added more complexity until we reached a point where we had data sets that had connected tables, for example, admissions and lab tests. Which was the final experiment that we did, and representing more complex data like the data that we would find in healthcare. And it's also worth noticing the approximate duration for each experiment. And you can see that it gets very CPU intensive very quickly. And to scale the approach up to create tens of thousands of data points would need days, which is a significant overhead, but not a prohibitive overhead. And we did have a dedicated a machine with 3 GPUs. It was a quite intensive process. And also the approach used 3 different data sets. We used open data sets in order to test transferability. But the main data set that the final experiments focused on was the MIMIC3 data set, which we thought was the most complete and most representative of what we wanted to do. This is just an overview of the hyperparameters of the last experiment. 50,000 epochs, the ReLU activation function, 2 hidden layers, Wasserstein distance, ATEM optimizer, and penalty of 10. And the data sample was 300 patients who had 379 admissions to hospital. And then these 379 admissions corresponded to 1,357 lab items and ICD-9 codes. So again, you can see that with relatively few patients, we get lots of lab tests codes and ICD codes that increase the computational requirements of the experiments. So again, with thousands of patients, this would need days. We did perform less accurate experiments with thousands of patients, and they were taking days. The next step of the method was to look at evidence of statistical equivalence between the synthetic dataset and the real dataset. So we're trying to figure out what kind of evidence would be sufficient to support assurance for the use of synthetic datasets. And we quickly realized that it's not a single piece of evidence, it's a combination of evidence that would provide the most assurance for that. We visualized the loss function in order to provide, to demonstrate that the generative adversarial network followed what theory would predict. So let's say provide some sort of confidence that we have there is a determinism in the approach that we followed. We did generate pair plots of real and synthetic data sets. We looked at the pairwise correlation between the two data sets, and we used correlation matrices, that's hundreds of rows and columns big. We used a non-parametric tests, the Mann-Whitney U-test, and finally we used Jacquard similarity. This is the this project focused mostly on the machine learning aspect. We found that without understanding the some tests of statistical equivalence, it's very difficult to come up with the right specification for the machine learning approach anyway. And that's why this was also a contextual step that provided requirements to the machine learning approach. But we also found that although we could demonstrate a degree of statistical equivalence, this field, this topic of research, synthetic data set, is in need of standardization. So it's a good idea to standardize what kind of statistical evidence would constitute acceptable assurance that two data sets are equivalent in the context of this specific use, validation of applications and regulatory approaches. So I'll go through the results of the project, the experiments that we run. So this is these are snapshots of variables through different stages of the neural network training. And I also forgot to mention that we implemented 3 different versions of generative adversarial networks. We used a vanilla GAN, a conditional GAN, and the Wasserstein GAN. And in the end, the Wasserstein GAN was the most appropriate one to use and produce the best results. And you can see how the synthetic data set, which is in orange, evolved through the iterations. So you can see how we started with some random values, and then as we trained the neural networks, the orange data points sort of aligned with the blue data points, which are the represent the real data set. And also you can see the performance of each implementation, and in this case the conditional GAN did not perform very well. We used this test for a quick trial and error, and it proved very effective. And this particular series of images is on mimic3 numerical data. And we have the same, we did the same for categorical data. We started with random values, and then the networks started generating synthetic data sets that looked closer to the real data set. In this case, the vanilla GAN didn't perform very well. The Wasserstein GAN performed better. So it gave us a strong indication that this would be the most suitable candidate. And we use this test because, as I said earlier, this can be computationally intensive. So it needs a little bit of time investment. So when you do trial and error and we need to adjust the hyperparameters, these runs may take hours or even days. So it's good to have an indication of what might work or not. This is another example of the results. This is a pair plot of numerical data. We have lots of pairs of variables, and this was not on mimic. No, it's the admission time and discharge time and so on. So these are just random variables that we picked to see if they were represented correctly in the synthetic data set. And you can see the distributions of the visual representation that are quite similar in the real data, which is the blue figures, and the synthetic data, which is the gray figures. Again, we use this as an early test to see which approach would perform better. This is the loss function, visualization of the loss function. In theory, the generator loss and discriminator loss should converge and reach an equilibrium where the generator produces data and the discriminator cannot tell if the data are fake or real. This gave us. This may seem like an obvious thing to do, but when we tried the different network configurations and the different GAN implementations, we got all sorts of different loss functions. So we weren't sure what exactly was going on behind the, let's say, the black box of machine learning, if we can call it like that. And it was difficult for us to explain how it would behave according to the theory. So although this is an obvious, it seems like an obvious thing to do, it gave us confidence that what the theory about neural networks was saying was what happened in our experiments. And this convergence between the two loss functions was an important aspect of the experiments. This is the correlation matrix between the data sets. It's a Spearman correlation. This is just an extract of the correlation matrix, just 10 ICD-9 codes and 10 lab item codes. But the actual matrix was, I think, 1,000 rows long and 1,000 columns wide. But you can see that the correlation between the variables, so the features that we have, is similar in the two data sets. So you can take, for example, this one, which is 0.022, and in the synthetic data set is 0.024. And this indicates that the variables as represented in synthetic data sets have maintained the correlation qualities amongst them. Now, there is a topic of debate here because the correlations are not identical, which actually is a good thing in terms of privacy, because it shows that the synthetic data set has produced somewhat different results. But we also, there's a question of tolerance. So we expect the synthetic data set is going to be slightly different, but there's a question of how much different can we tolerate before we can say that the synthetic data set can no longer represent the real data set. That's an open question. We don't have any recommendations for that, except that it has to do with the specific application that's validated with the synthetic data set. So it's context specific, but we haven't explored this question much. And finally, the Jacquard similarity. We looked at the Jacquard similarity of ICD-9 codes and lab item codes, and most of the variables where they had a hijacker similarity that indicates that the synthetic data set is statistically equivalent, is a subset of the real data set. Now, I mentioned that all the motivation of all this was to try and establish assurance and validate digital health applications and digital health innovations. So, and we also had a step that looked at the safety assurance aspects of this and informed some of the steps of the synthetic dataset generation method. So this is what we call in safety engineering an assurance argument, and we use this notation we call goal structuring notation to visualize the argument. I won't go into details, but it's a fairly standard practice to doing safety that helps readability of a safety argument. And essentially, we make claims about our experiments and our applications that we are prepared to defend in after the application has been validated. So we come up with potential goals, post conditions, if you will, that the evidence that we will gather throughout the process will allow us to substantiate and support with sufficient assurance. So the first claim, the obvious claim to make is that the smart application, the innovation, if you will, is acceptably safe. And we identified as claims, subclaims supporting this, this argument that we will need to justify the acceptable risk because all systems, all software will have some residual risk, so we need to justify what is acceptable. We need to identify the risk, we need to monitor the risk, and we need to balance the risk against the expected clinical benefit. And actually, this is the kind of argument that you will see is being required from regulation, such as the medical devices regulation, which is applicable in the European Union. And we also have in the UK the NHS digital standards. We have the ISB standards that also ask for something like that. And we also need to see how the new UK CA approach will implement this or not. We also need to look at the clinical basis for justification of data. So what is the what are the guidelines telling us, the literature is telling us, and whether this may be in conflict with what the innovation is recommending. So if we have clinical best practice guidelines that say A and the application that we do says B, we need to understand why there's this difference. And then we need to look, and I have this in gray because we didn't look at this at all. They were outside the scope of the project, but we looked at potential risks. So we need to identify the risks of an innovation, and we need also to justify the suitability of evidence for the identified risks. So in other words, when we have an innovation, we will say that we have validated this innovation using the synthetic data set, but we also need to explain why this synthetic data set is appropriate, is suitable for this validation. And this is where it relates to the synthetic dataset generation method. Then, as we try to develop that argument further, we came up with sub-claims, sub-arguments, if you will, that about the statistical equivalence of the realistic synthetic data set and the algorithmic justification of the machine learning approach, or if you prefer, the explainability, although explainability in the literature is much more composite and consists of more steps than just looking at the algorithm. And then we looked at how we can support these claims using the evidence that we produced throughout this approach. So, for example, Jacquard similarity and the correlation matrix of the two data sets can be used to support statistical equivalence between the two data sets. And the loss function behaving as expected could provide some evidence about the algorithmic justification of the approach. And again, there is a question of what data we need and how much, what evidence we need and how much evidence will be sufficient, which are questions that we need to explore in the field. So just to wrap up and conclude, we wanted to look at whether we can create a synthetic data set that could be used to validate digital health innovations as part of safety assurance and regulation. The use of synthetic data sets to overcome some privacy concerns seemed promising. The approach that we followed, and particularly the use of generative adversarial networks, seems very promising. At the end of the project, we thought that this could be a good way to continue. There was some evidence supporting the equivalence of data sets, but we need more standardization of what is acceptable in terms of statistical evidence. The machine learning approach may introduce its own issues, and we need to be careful of that. For example, representation of minority groups or outlier data points. We need to confirm that the synthetic data set has included these aspects. We did identify a few ways that could potentially be used to provide evidence that this has happened. But again, this was outside the scope that focused on the machine learning bit mostly. There is significant processing power needed in order to perform all these experiments, but it's not prohibitive. So we used a fairly state-of-the-art standalone machine with 3 GPUs. It was taking a lot of time, but these days with much bigger machines, use of cloud processing, we don't see this as being a major issue, although it needs to be considered. Although the synthetic dataset contains fictional entries and fictional data points, completely made up, there is a question of whether the real dataset can be extracted using advanced mathematical techniques. This is a concern. It's not a deal breaker of the approaches at the moment. But more advanced privacy techniques will eventually need to be employed to provide further assurance on privacy. For example, differential privacy provides some sort of mathematical approaches that may offer good assurance on privacy. Synthetic datasets seem sufficient for early de-risking of healthcare innovations. A regulatory / assurance approach could accommodate them standalone if it's a lower criticality application or in combination with real data. We think that this could be a way forward, and it will catalyze innovation a lot and will allow this sort of self-assessment, self-validation before applications go through the formal validation and formal regulation. Because that's something else that we have noticed. In our experience, there are many innovators in healthcare. They do focus on the clinical bit, and when the time comes to go through the safety validation, then this becomes a little bit more challenging, and they need to go back and redraw some of the designs that they have made, resulting in overheads. And we also found that a lot of literature on explainability of machine learning relies on good initial data sets. So they focus a lot on the quality of the data set and the curation of data. And that's why we think that a good evidence supporting the synthetic data sets will also ultimately help the explainability of machine learning when the machine learning approaches have used the synthetic data sets to get validated or to train themselves. This does not apply for when generating the synthetic data set. And also, because I mentioned about regulation and safety assurance, just a disclaimer that this was a research project, and our partners, what we say in the results and in the presentation does not reflect the position of the partners or organizations who were involved in this project. This is just our own views as a university and as a research project. So thank you for this, and I have a couple of publications that summarize the results in more detail, and I think it's time to give the floor for discussion, to open the floor for discussion.
That's great. Thanks, George. And we've got some questions in the chat. I'll do the emceeing if that's okay with you, George. So the first one we've got is from Gillian Rabb. But this is interesting. We need audience participation here because she's got in big capitals. Would like to expand on what I mean. Gillian, would you like to expand on what you mean?
Thank you. I didn't mean capitals. Can you hear me all right?
Yeah,
Yes.
perfect.
I was interested to know how you dealt in your synthesizing your data. The plots you showed us seem to be just one measurement per individual, but your data are clearly highly structured. So you have a list of, say, tests for each individual, presumably indexed by time and so on. And I was just thinking that algorithms like that presumably make use of things like changes in, say, blood pressure from one time to the other. If you're writing these kind of algorithms, were you able to represent that in modeling your synthetic data, and in particular in the loss functions you were using for comparing? Just be interested. I've done a lot on synthetic data, but I know this kind of data is very challenging.
Yes, the short answer would be no, because we didn't represent the time function in the experiments. So how data may progress through time, we didn't look at that. But we looked at the sort of flat representation of a time instance that we would get from Mimic 3.
Right. Yes, I've written a paper on utility, how to measure utility of synthetic data. You might be interested in. I put it in the chat.
Okay, that would be interesting. Thank you.
Yes, but just to follow up very briefly on that, are you aware? Have you studied the algorithms that are used? You know, that you're training your data set for, because that would be important. You know, what
you mean the algorithms for the applications?
Yes.
That's the answer to this question is very big. We did have pointers from an industrial partner on what a typical application might look like and what algorithms it might use. but we did not test it for a specific application. One of the issues that we had was that we needed to make a decision early on whether we're going to be context specific or as context independent as possible. And we went for the latter. That was done intentionally just to focus on the machine learning approaches, to test them, and then to test how we would validate equivalence of the data sets. We had pointers from real applications, but we didn't look at how they would use the data.
Thanks very much. And I'd love to see how get some references to your papers.
Yeah.
Very interesting talk. Thanks.
Great, lovely. So the next one is from German, and I'll just shout this one out. You're welcome to interrupt. Does the model only learn the relationships between columns? So any row dependencies, including over time, like multiple admission episodes forming continuous stay or multiple drugs being co-prescribed in a short period of time, are out of scope?
Yes and no. We did not look at how the data would change over time, but the synthetic data set was able to capture the multiple drugs being prescribed and the multiple ICD-9 codes, for example, due to comorbidities. So actually, we did a manual review of the results to look for comorbidities and the drugs, and we managed to find that the synthetic data set captured this well enough, but we didn't perform a statistical test to check whether these were being completely accurate. So no over time, but the GAN did replicate these, comorbidities and the multiple drugs.
Right. Next one is from Grant Mayer, our very own Grant Mayer in Edinburgh. How far off are we for doing this for imaging data?
I would say, in my opinion, we're very close because particularly GANs started from imaging. So GANs do perform a lot better with images. So we think that they're going to perform well for imaging data. We would like to test this, but so far this is just our gut feeling. We haven't tested it, but given how good GANs are with images, we think they will be suitable for imaging data as well.
Right. Okay. There's a little bit of extra stuff in the chat with some input to that. But the next one I think is Liz Elliott. Did you take any additional steps to increase privacy for rare conditions or events? You might need to elaborate on this, Liz. I'm not sure.
I think the rare conditions have to do with the outliers and the data points that are more easily identifiable. Correct me if I'm wrong, and you don't mean that. But the answer is no, we didn't look at privacy for rare conditions. We looked at the synthetic data set and we confirmed that all data entries were different. But other than that, using some more advanced mathematical approaches to reverse engineer the real data set, we didn't look at. And that's why we also recommended that approaches like differential privacy could be very useful for synthetic data sets, particularly when they're produced using machine learning.
Okay. Next one, I think going through is there's quite a lot of information in the chat as well, which is a good thing. Next one I picked up is from Sophia Sanabria. Could you please mention practical real use cases of your work on validation? So she's working on a applying the synthetic data to test recruitment systems in a realistic environment? I don't know, Sophia, you may want to elaborate on this. Please, people, feel free to jump in if I'm not representing your question well.
So use cases can be any application. I think clinical decision support, applications that use machine learning, symptom checkers, they are trained on using big data sets. So any application that may need to be trained on big data sets could make use of the synthetic data sets. I mean, even if a developer has access to their own data set, it's a good idea to have a second data set to confirm and remove potential biases. And just to answer to the other questions, and no, we did not use the time series. This is quite interesting. We identified some potential approaches for that, but this would need to be a separate project. And yes, we started with a Mimic3 dataset. Yeah, everything that we had was anonymized.
Fantastic, and you're ahead of me, George. It's, you got the question out ahead as well. I'm wondering. Oh, here's another one popped in. Wait a minute. I thought we were sort of at the end, but we're not quite. So one from Sam Danzo. Would you say that true validation would be checking the performance of the models between real data versus synthetic data? So you have to go back to the real data.
I'd say that this kind of condition would cause a lot of debate, because it's a little bit of a chicken and egg thing, because if the performance of the model is not good, then maybe it's the model or maybe it's the data set. If that was the case, I would definitely look at both. However, what we focused on was the equivalence of the real data set and the synthetic data set. And we think that the performance will be close enough. And if there is an issue in terms of with the data set and not with the model, then the issue would probably be with the real data set. Well, assuming that we have demonstrated equivalence. Unless, of course, there are some other statistical tests that may demonstrate that certain other attributes or statistical attributes have not been emulated well enough in the synthetic data set. So far, the evidence that we have for the synthetic data was good enough. So in such a case, we would say that the first thing that we would look at would be the model, and then the real data set and whether it was representative enough. And perhaps there are some statistical tests that we would need to consider to increase our confidence in the synthetic data.
Okay, and I think that's the end of. Actually, am I allowed, George? Can I ask you a question? Do you mind? They're not. It's not on the list, but it's on my mind. So just to finish up with, and this may be showing my complete ignorance of this domain. I'm sorry. So when you were talking, I was thinking about this, and the reason I'm asking you is because you're very interested in the kind of in being able to show that it is true, the certification side, and be able to talk about the risks and all of that. And yet you're working with GANs, so you've got machine learning on both sides. So is the argument that you would make for this, because you want to be able to show, well, it's not going to reveal anything that we don't want to reveal, plus we want it to be the representative of the data set. For that second bit, forget the first bit, for that second bit, where you've got your adversarial network doing the checking. What is the point at which you're happy to certify? How do you show that you've hit the point where that's good enough? Or am I asking a stupid question and there never is a point where you can do that?
No, and I think that that can be combined with Sophia's last question. We don't know. So
yeah.
we have so there are two issues here. One is the machine learning approach itself, which is a bigger challenge in the domain and the explainability of machine learning and safety certification machine learning. And I will leave that on the side for the time being because it's
very difficult.
Yeah, and then the evidence that the synthetic data set is good enough. We picked some statistical tests that we found in the literature, but I think this needs to be studied more rigorously and identify potential, let's say, statistical failures between the two data sets and see which what kind of evidence would support an argument that these failures have not occurred. And that's why I mentioned, and this comes to Sophia's question, that standardization is needed. And it's both from a statistical point of view and the community, because the community usually in those things will converge into what they think is acceptable and sufficient evidence. And perhaps we could work towards a standard of what is sufficient statistical evidence to compare synthetic data sets, to validate synthetic data sets against the equivalent real data set. So I think this is the biggest open question at the moment. We may have enough evidence already, or we may need some additional statistical tests to increase our confidence in this.
Yeah, terrific. Well, I think that concludes our questions, and actually we're nearly out of time anyway. So all that's left to me is to thank you, George, for giving your very thought-provoking talk. People can see in the chat, Serena has added in the next ones in the series, so I hope people will be interested in coming along to that. Meanwhile, thanks very much for everybody for participating, and enjoy the rest of your evening. Thank you very much.
Thank you for having me here.
Bye.